Hello and welcome to Chemistry with Dr. Clark. In this video, I would like to talk about LeChatelier's principle and how we would predict whether a reaction would move forwards or backwards, forwards or reverse, depending on how we stress the equilibrium. Now, I've broken this video up into a couple of parts, mainly because the changes in concentration and temperature tend to go together. So I'll do both of those in part one. And then in part two, I'll talk about pressure and volume. If you change the pressure of your equilibrium or you change the volume of its container, those two also tend to go together. So I'll split it over two videos. Part one will be concentration and temperature. Part two will be pressure versus volume. And I've got the link to part two in the description below. Okay, so let's define LeChatelier's principle. LeChatelier said, if you have an equilibrium, like this beautiful equilibrium here, I have some sulfur and some oxygen. They come together to form sulfur dioxide, and then the sulfur dioxide falls apart and turns back into sulfur and oxygen. So the reaction goes forward, and then the reaction goes backwards. Reaction goes forwards, reaction goes backwards. Right? Sulfurs and oxygens come together, sulfur dioxides fall apart. This is a lovely equilibrium. Right? It's totally happy, it's coming together, it's falling apart, it is stable. And then you, a mean, nasty chemist, comes along and decides, I'd like to poke at that equilibrium. I would like to make a change and see what happens. Okay, so you had a lovely equilibrium, and now you've decided that you're going to make a change. And the change will either be concentration, you add more or take away some of a chemical. You change the temperature, you heat it up, you cool it down. Or you change the pressure or the volume. Okay? And what LeChatelier said was, no matter what you do to this equilibrium, it will always attempt to undo it. If you add more sulfur, it's going to try and get rid of sulfur. If you increase the temperature, it's going to try and decrease the temperature. If you decrease the volume, it's going to attempt to increase the volume. No matter what you do to the equilibrium, it will attempt to undo it. Okay? So if stress is applied to a system in equilibrium, the equilibrium changes to relieve the stress. Okay? You apply a stress, you apply a change, and it's going to attempt to undo the change. It's going to attempt to relieve the stress. Okay. So let's talk about the first stress that we can apply, changing concentrations. So what I've got here is kind of a table that will summarize. Okay? So it says reactants versus products, adding versus removing. So if you were to take reactants and you were to add them, your reaction for a small while is not going to be in equilibrium anymore. You're not going to have both forwards and backwards. For a little while, that gets destroyed, gone. And for a little while, only the forward reaction happens. So for a little while, the reaction will only go forwards. Reactants will turn into products. Okay. Let's say that if you had reactants, but this time you're removing them. Okay, reactants removing. Again, you had an equilibrium going in both directions. The minute that you remove a reactant, the equilibrium stops, gone. And for a small amount of time, the equilibrium is only going to go backwards. So if you remove reactants, the equilibrium will go backwards. So products will turn back into reactants. Okay, same thing with the products, right? If you had products and you're going to add them, for a small amount of time, the reaction is going to go backwards. So that's how this table works. It's a bit of a summary. So there's two ways to do these problems. The first one is you could just purely memorize the table, right? So this little table here, you memorize it. When you go to do a test or go do an assignment, what you do is you just rewrite it right on the side of your paper and use it. So if someone says you are going to add products, you know that the reaction is going to go backwards. Or if someone says you're going to remove reactants, you know it's going to go backwards. Okay, that is a perfectly acceptable way of doing this. You just memorize the table and you use it. The other way to do this is to think about the change you're making And how would you undo the change? How would you compensate? Okay, so let's talk about these two reactions. Let's say for the first one, I've decided the change I'm going to make is that I'm going to add NH3. So if you use your table, I am adding product. Okay, so product, adding. If you add product, the whole thing should go backwards. Okay, so you would say the reaction's going to go backwards, or you would say that the reverse reaction is favored, right? Or you could say that the reactants are favored. So you could say reactants are favored, right? There are a couple of different ways to show it. So if you've decided that the whole thing is going to go backwards, you could just draw an arrow showing backwards. And that shows that the reaction is going backwards. Or you could say reactants are favored, because if this reaction is going backwards, what are you making? Making reactants. So the reactants are being favored. Or if it's going backwards, instead of just drawing the arrow, you could use your words and say, well, the reverse, the backwards is favored. Now, let's talk about what this means in more practical terms. This is an equilibrium. In the beginning, you had a little bit of nitrogen, you had a little pile of hydrogen, and you had a little pile of ammonia. Okay? So the nitrogens and the hydrogens were coming together to form ammonias, and the ammonias were falling apart to turn back into nitrogens and hydrogens. Okay? So they were coming together, and then they were falling apart. Coming together, falling apart. But you always had a little bit of all three. A little bit of N2, a little bit of H2, a little bit of ammonia. Now what you're doing, you're saying, oh, let's add some NH3. So I'm adding NH3, I have more of this. Well, now you've got way too much product because you had some product. Now you've added more product, and now you got too much. So if you have too much product, how are you going to get rid of it? The only way to get rid of extra product is to turn it back into reactants. Make the whole thing go backwards. Right? If you got too much product, the only way to get rid of product is split it up, turn it back into reactants. Now, when we talk about it undoing the change, you never get back to what you originally had. Right? If I had a bunch of extra product and I turn it back into reactants, that will reduce the amount of extra product, but I'm never going to get rid of all of it, right? I'll always have the original plus a little bit extra. Not as much extra as I added. It's like you started with this much, you added more, you got rid of some of it, but you never quite get back to where you started. And if this reaction is going backwards, I'm going to be making reactants. So I'm going to have extra N2 and I'm going to have extra H2. So when we say that this tries to undo the change, it will undo the change somewhat, but it can never bring it back to the original conditions, right? I can bring down that extra product, but it'll never be back down to the original amount. And I'll never have the same original amounts of reactants because I'm going to make some, right? So that amount is going to go up. All right, for the second one here, let's say that we are going to remove, let's remove some product. So let's remove some PBr5. So if you're going to use your table, this is a product, and you are removing it. So products removed, it should make the whole reaction go forwards. Now, you know what the words are going to become. If backwards said the reactants are favored, the forwards is making more product. So you're going to say that your products are favored. Or you're going to say that the forward reaction is favored. So forward reaction is favored. Right? They're just totally opposite. Reactants were favored, now the products are. Reverse reaction was favored, now the forward is favored. Instead of the backwards arrow, you got the forwards arrow. Now, for most assignments, you don't have to write all three. If you show the arrow pointing forwards, That means the same as saying products are favored, which means the same as saying forward reaction is favored. Okay, so you usually don't have to give all of them. You just have to give like one of the three. Okay, that's just using the table. But again, let's sort out what it means. Right in the beginning, you had a little bit of this reactant, you had a little bit of this reactant, and you had a little bit of your product. Right, you had a little bit of each. And by removing this, it's like saying, oh, we have removed some of this. Well, if you remove some of this, now you don't have enough, right? How do you undo losing some of your product? Well, you got to make more. How do you make more product? You take some of your reactants and you turn them into products, right? Because I removed some. If you remove some of your product, how do you get it back? You take reactants and make more product. That's why it's the forward arrow, right? Because you're trying to replace what was lost. And the forward reaction, taking reactants and putting them together to make products, will replace what you're lost. Okay, that is changes in concentration. All right, so let's talk changes in temperature. All right, let me move this around a bit. Okay, now again, I got a table for that. If your forward reaction is endothermic, then I say what happens by increasing the temperature or decreasing it. If I say that your reaction is exothermic, again, I say what's happening if you increase the temperature or decrease it. So let's say we talk about this first one here, okay? This first reaction has some H2 gas reacting with some NO gas, turning into water gas and N2 gas. And I've got heat written here as a product. If the heat is written here as a product, this is an exothermic reaction. Now, I should probably say the heat is a little tricky. Like, we don't always put it in the same way every single time. So if you look at the three examples, see here I have the heat as a product, and I actually tell you how much. Okay. See, in the next example, I have the heat, but instead of telling you how much, I just use the word heat. So instead of saying plus a certain amount, I've got plus heat. Okay, so you don't always have to give the actual number, you just could use the word heat. Now, if the heat is on the product side, it's exothermic. But if the heat is on the reactant side, right, the heat's over here with the reactants, then that is endothermic. And sometimes I'll just use the word and I'll say, hey, see this equilibrium? It's endothermic, right? So sometimes I'll just tell it to you. Okay, so for the heat is not super consistent. Sometimes we include it in the reaction as a number. Sometimes we include it in the reaction as just the word heat. And sometimes we don't include it in the reaction at all. We just use words in the problem to tell you what you got. Like the problem will say, consider the following endothermic reaction. Well, then you know it's endothermic. Okay? Now, once you know what it is, then you can tell what's happening by whether the temperature goes up or not. Let's say for this exothermic one. Let's say for this one, I am going to increase the temperature. Okay, so if we look up here, here's exothermic. Here's increasing the temperature. So exothermic, increasing the temperature. It says that this equilibrium is going to stop for a few minutes and the whole thing is going to go backwards. You are going to favor the reactants. You are going to favor the reverse reaction, right? Exothermic, increase the temperature. There's your answer. Just like the last time, you can memorize the table, write it down on your page when you're doing a test or a quiz or an assignment, and then you just look them up, right? Exothermic, check. Increase the temperature, check. Where do they meet? Backwards reaction, okay? If we do the same thing for the next one, okay, let's say that this one I'm also going to increase the temperature. Okay, so for this one, it's endothermic. So endothermic, increase the temperature, increase the temperature. So where does endothermic and increasing the temperature meets here. And this says for a little while the equilibrium stops. So instead of getting reaction going in both directions, you only get the forward reaction. All right, and if we try the third one there, this one's endothermic, and let's say this time we decrease the temperature. Okay, so here's endothermic. Here's decreasing the temperature. Where do the two meet? Meets right here. So if you've got an endothermic reaction and you decrease the temperature, the equilibrium will stop. So instead of going in both directions, it'll only go in the reverse. So if you're doing LeChatelier and you've memorized the table, these are very easy problems. All you have to decide is exothermic or endothermic, increase the temperature or decrease the temperature, and then read it off your table. The reason why I like to put this and concentration together, though, is because they you can think about them the same way, right? So instead of memorizing the table, if you just want to think about it as undoing the change. Okay, let's talk about this equation. In the beginning, you have some H2, you have some NO, you have some H2O, you got some N2, but you've also got some heat. You can consider the heat to be like a chemical, right? I had some reactant, some product, some heat, right? You can consider the heat to be like any of the other chemicals. You just have a pile of it. You have some. Now, what does it say that we're going to do? Increasing the temperature. If you increase the temperature, that's like adding extra heat, right? Increasing the temperature is adding heat. You now have too many products, right? This product stayed the same. This product stayed the same. This product you now have extra. And if you have too many products, how do you get rid of products? You turn them back into reactants. You go backwards. You're going to take some of these products and turn them back into reactants. And like I said before, this whole thing is an attempt to undo the change, but you never get back to the beginning, right? I had heat. I add a temperature which increased the heat. By going backwards, the heat will drop, but it'll never drop back to where it was. Okay, it'll always be a bit higher. And it's going to mess with everything else. Because if I'm going backwards, I'm dropping the amount of heat, but what else am I dropping? I'm going to drop the amount of N2 and I'm going to drop the amount of H2. So even though I didn't stress these two, even though I didn't do anything to the water or the nitrogen, they're both going to drop as well, right? Because the products are all going to drop. What's going to happen to the H2 and the NO? If you're going backwards, you're making them. So the amount of H2 will go up, the amount of NO will go up, right? So in order to counteract the change, you are going to change everything, right? Our main focus was to undo this. So you added extra, so you had to get rid of it. But by doing that, you change everything else, okay? So let's move on to the next one. You had some carbon dioxides, you had some waters, you had some heat, right? A little bit of each. And on the product side, you had a little bit of the glucose and a little bit of the oxygen, right? You had some reactants, you had some products. Reactants came together to form products. Products fell apart to form reactants. And again, you're going to make more of something. You're going to increase the temperature. So you now have more heat. You now have too many reactants. If you've got too many reactants, how do you get rid of extra reactants? You turn them into products. Forward reaction, right? How do you get rid of reactants? Turn them into products. Because by turning it into a product, you're going to use up your reactant. So the amount of heat starts to drop again. You'll use this up. Now you're also going to use up the water and the carbon dioxide, so these will also drop. And you're making products, so the amount of products will go up, right? Everything will readjust a little bit. But the main thing you're aiming for is to take the amount of heat that was increased and drop it back down. All right, and for the last one here. You had some carbon dioxide, you had some carbon, you had some carbon monoxide. Now, if you're going to do this by looking at what's going up, what's going down, and how you're going to counteract the change, really, this heat has to be built into the equation. right? Here, the heat was built in as a product. Here, the heat was built in as a reactant. Here, the heat needs to be built in. So when I tell you it's an endothermic reaction, that means your heat is a reactant. So I can write it here as heat plus, right? I can consider it as one of the reactants. So if it's endothermic, the heat shows up as a reactant. If it's exothermic, it's a product. Now, I don't know how much. That's why I just called it heat. So I said heat plus. So that way I can say, hey, I got some heat, right? What's your reactants? Carbons, carbon dioxides, and heat. Now, what are you doing here? I'm decreasing the temperature. If you drop the temperature, what you're doing is sucking heat away. So I'm canceling this out, right? Canceling some of that heat. Well, now you don't have enough reactants, right? You used up some of your reactant. Your reactant is gone. How are you going to make more reactants? You're going to have to take some of your products and turn them into reactants, right? Because if you take your product and turn it into reactants, you're going to replace them. You'll replace the heat that you lost. So the reaction will go backwards. Backwards. Now, as you go backwards, you will be making reactants, right? Because it's going this way. So you will replace the heat that you lost. But you're also going to increase the amount of carbon dioxide, you're going to increase the amount of carbon, and you're going to drop the amount of carbon monoxide, right? Because if you go backwards, you're using up products. So you're going to undo the change, but you never get back to where you started, right? If I had this much heat and I dropped it, by going backwards, I can replace some of it, but I'll never end up back to where I was. So that's Le Chatelier if you go changing concentration or if you go changing temperature, right? Those are two of the four stresses. When we talk Le Chatelier, we like to talk about stressing the equilibrium. So you can stress it by changing concentrations, or you can stress it by changing the temperature. And they do work kind of the same. They're a nice pair. In the second video in this series, I will talk about changing pressure and volume. Those are different from these two, but they are very similar to each other, and that's why I've got them lumped together. So I have the link below in the description. Please take a look at that. And as always, thank you for joining me here at Chemistry with Dr. Clark.